So I hope you see my screen now. And well, let's go on. So today's lecture in QBI, we're going to talk about ground truth and building and augmenting data sets. This is a topic which maybe looks a bit strange, possibly. So anyway, we are going to talk about different types of data sets, also about a topic called augmentation, and finally about baselines. And first we need to load some notebooks before we, or some modules before we start the lecture. So again, these modules will be used throughout in the code segments. It takes a little time to load it right now because there are some which are quite large. For example, this Keras is pretty large. It contains a lot of images, and that's why it takes time. And now we got it. And let's see, we have the next slide. No, so next slide. So there are some material that you can read, and it's good background material if you want to read on this. So the question is now, I'm saying we load a lot of data, we actually will look at other people's data. So why do we do it? That is a good question, and also you already have your data, so that's probably also the reason why you took this class in the beginning. So before we start looking into the data, there are some quotes from people who has something to say about data, and these people are from different data scientists at Facebook, for example, this one. This guy, he thinks, well, he loves working with all these fantastic AI algorithms, but in the end, to be honest, he more or less says that he has learned a lot more from just looking into some few data sets than all the fun algorithms that he has trained and combined, because there's a lot of combining when you do machine learning. So this gives us the first hint on that the data is a very important thing when we talk about data science, image processing, and also for the quantification of our image data sets. Another thing, which is the director of the artificial intelligence lab at Tesla, that is also quite telling story, that many PhD students, they have many sleepless nights about models and algorithms, how to do stuff, and very little about the data, because the data is very scarce in many PhD projects. You get maybe 1-2 beam times, and with that you create all the data that you will work on for the whole PhD. At Tesla, they have completely different approach. They have a lot of data. So actually what people lose their sleep about is the data sets and less about the algorithms. So they focus a lot more on the data than on the algorithms. And then we come to this lady, also an image analytics person at Planet Labs. And well, she has a lot of tweeting, and in the end, she comes to the point that 95% of her job is about preparing and making data available. And finally, the last 5% is just putting the data through the algorithms that she has set up. So you see already here that in machine learning, there's a big focus on getting the data in a good quality, because the better quality you have on the data, the better outcome you get afterwards. And the same is also actually also on traditional image processing, that make sure that you do a really good experiment, providing you with a lot of relevant data. So let's go on. Data is, data is, as you have seen, a very important thing, and some people even claim it's the new oil of today. This paper that is linked here on this slide actually claims it's not the new oil, because oil is a consumable resource. So once you have consumed it, you can't reuse it. But data, on the other hand, is something you can, if you prepare it in the right way, you can actually work with it several times. Many people can reuse your data if you make it available. And it's important to have also data for just testing your algorithms. So if you don't know what you expect, how can you know that your algorithm is actually doing what you expect it to? If you have a lot of edge cases, that means essentially outliers in your data set, that this one is extreme in that sense, and the other one is extreme in the other sense, then you can hopefully create a model that works for everything, but you have to make sure that you have everything in between too. So you need to build your data set pretty largely. Also, in some cases, in particular in the large companies, then they have a very rapid development pace on the algorithms. So apparently at Facebook, they have new versions multiple times per day, and their apps maybe also every day. And that means there is ongoing changes in the algorithms, and you still need to be sure that the algorithms are doing what they are supposed to. Also, for machine learning, you require good data, because without it, the methods can't learn. So you really need to provide some kind of ground truth to teach these methods. So if you want to count cells, you can write your own algorithm, or you can also, that would probably be pretty easy actually. That's a few steps. But if you want to look into what happens with these cells, then it's much more difficult, in particular if you have some fuzzy relations to what you want to tell about them, these subtle changes. And that is actually also, again, one of the frustrating things about image processing. You can, with qualitative analysis, you can say, okay, that cell changed a little bit to that shape, that is roundish, that is more elongated. And in order to bring this in, it's really important to have data that are related to all these features or variations that you want to describe. Data is, as the author of the Is Not the New Oil paper, reusable. In principle, if you have it on the hard drive, it can be reused by those who have access to this hard drive. Or if you put it in the cloud, of course, even more people can have access to this data. And the important thing about making it reusable is that it needs to be well organized, with good labels, with good descriptions. And if you have that, it's very easy for someone else to take your data and combine it to get better results on their algorithms. So maybe they only have a little data set, but with the help of your data, they can improve their algorithms a lot. And in that sense, they can also get better conclusions on their own data. Then the other problem is that algorithms are often only prototypes, because you don't never have time to do anything more than a prototype. So it's usually messy, it's complicated, because you see, if I do this, then I need to add this case, and if I do that, then I need to add that case, and so on. It's also maybe not so well documented, and in general well written according to styling rules, etc. And this in particular applies to students who want to get results on time. They don't care really about having nice software engineering, because it's about getting the data, getting those plots out for the thesis or for the paper or something. And in that sense, it's also good to have some reference to check that your algorithms are actually doing what it's supposed to. And some of the famous data sets that we will encounter are, for example, the MNIST digit dataset, the Imagenet. There is also one called BRATS from medical imaging. And these datasets are very important when you try to train your image processing or image analysis workflow and network training, etc. So the MNIST is a database of well-prepared numbers, digits, handwritten. So we have the digits 0 to 9, each with its own label. And as you can see, this is a very beautiful black and white, maybe with some smoothness on the edges, but in general, it's pretty neatly prepared already. There is no noise. So it's very easy to use this data set. Also, if you want to, in real world, you may have different illumination conditions and noise and everything. This is anyway a good base to get the basic foundation for your algorithm. If it doesn't work on this, how can it work on something that is real? Another one is the Imagenet. It's a very large database, and it's organized in the same way as another database called WordNet. So it's really hierarchically organized into different categories. So this is a bit small, but you have entity, then you have objects, and substance matter. And then on objects, you have organisms and artifacts. And then it goes down along this tree structure. And then in the end, for example, you have different males, you have boys, and you have girls, and John and Mary, if you are going really detailed. And this database is used as basic training for natural picture categorization algorithms. So you can also, with this, you can look into, for example, checking if it's a dog or cat, but you can also check on different dog races, if it's a wolf or German Shepherd. And the algorithms have evolved over time. So the bar chart you see here to the right shows the status at 2010. Then you have an error rate of 28%. So that's not really convincing. But with time, they are now down to, or probably even further. This was 2015. So it's a pretty rapid development. In 2015, you have 3.5% error rate. So it was really much more safe to rely on the classification that these networks were doing. What you also can see is that the neural network used for this classification, because that is the method that has been used, was in the beginning very shallow. So a neural network has kind of an architecture where you have different layers where the data is pushed forward into. And in the beginning it was maybe just an input layer, some intermediate layer, and then output directly. Then they started adding layers within these models, and AlexNet is kind of a baseline today. I'm going to talk about baselines little bit later. And that one started adding a lot more layers within the network. And then the reasoning was that, well, if more layers are better, why not add many more layers? So in the end, they ended up in this ResNet algorithm, which has 152 layers built in. So it's the input and then 152 layers on the way. And then finally, you have the output, which tells you what it is. Another database is the BRADS, which is a collection of MRI scans from brains with tumors in them. I assume it also contains healthy specimens, because otherwise you don't have anything to compare with. It also uses different modes of the MRI to show different features, and that together will then be used for training purposes for different segmentation and classification algorithms. So what do we get from this? One is that data sets have actually changed the way how you think about how to work with the image analysis problem. And there are different ways to approach this. On one side, we actually need the information from domain experts who mark up the images, handcraft features. So marking up this, telling, for example, this is number 6 in the MNIST database, or this is a particle that is of relevance for nutrition transport in soil, or that is the tumor, or that is, yeah, whatever. So there are different features that different scientists, experts in their field mark up. And that is a very time-consuming thing. Then once you have all this data, then you can start doing machine learning methods. And then all of a sudden, you don't need any domain expertise because someone else provided it, and you can just train your networks based on this. And there are even competitions on how well you can classify different images. And there are even cases of like Russian teenagers who put together some network, and then all of a sudden they can win a contest on Kaggle. In the end, you need a more structured approach to have a robust outcome. But anyway, it is possible for someone with absolutely no knowledge to get really good results that approaches or maybe even exceeds what the expert would do if they do it by hand. And that will actually save you a lot of time when you do afterwards do the processing. So the question is now, what is this a machine learning course? No. And does machine learning always win? Well, it does actually provide very convincing results. But the important thing is that we need a lot of data in order to make the machine learning work. And that is very important, and important to the level that there are even papers about, for example, the FAIR principle, which means that the data that you have collected in your experiments should at some point be findable. It should also be accessible. Interoperable, that's an interesting thing. It's actually that it's possible to use it with common software and read in the images using some kind of image reader, and also reusable. But all this requires that you provide a lot of information around the data, not only that you have image label, but also the conditions when the data was acquired. What parameters did you change in order to get this condition? and so on. So there is a lot of considerations to think about. The FAIR principle is something that is actually a policy in Switzerland. So if you apply for grants at the national funds in Switzerland, then you actually have to have a plan how you are going to store and handle the data and making it available for later research. And that is also brought up on a higher level. So on the European level, there is also consortia that work on getting open data and making that a concept. So and all these work is based on this FAIR principle. So it's a very important thing to have in mind when you do your experiments. Please do a lot of notes about the conditions and make the data available. Also, publications actually also start asking for depositing the data that you used in order to produce your publication. Then there are also other data sets. Of course, there are pretty many. One thing is, well, on Wikipedia, always land on Wikipedia if you do a search, there is a list of different categories of databases. Another one which is very interesting is the Google dataset search. It is actually finding pretty much, but there you have to take a critical eye on what kind of data is it you actually are looking for, but because sometimes you get only a single data set, and that doesn't help you really if you want to use it as kind of a statistical evaluation for your data. This actually also brings us back to what I did last week with this smoke test analysis, that you actually can get real data from someone else to test what your algorithm is doing before you even let it run on your own data. So what is now a good data set? So in principle, a good data set is characterized by a large amount, there is diversity and annotation. So this means you can actually work with small data sets, but in principle, when it comes to data, the bigger, the better. It gives you more statistical variations. It gives you maybe headaches in processing it in time. But anyway, it will give you a more robust model if you can use more data. So the more complicated your problem is, the more data you need. And also, if there are very small changes, you really need to have a good base to decide what is now this piece which is of interest. For example, it's very difficult to separate a tumor against normal tissue. And sometimes it can even, the classification can even be in the wrong place. So maybe you're looking for a tumor in a place where it couldn't even be. The other thing is also if you have class imbalance, that's something I'm going to mention soon, then you have something very rare that you want to detect. And that's also a problem. And to capture that, you really need to have large data sets. Then diversity is, well, something that you really need too. It's you need many variations to really capture what you are seeing in your data in your experiment, but maybe even seeing a little bit more beyond what you expect to see, because otherwise you cannot capture those, or you will get misclassifications based on that. So, and also there are a lot of different methods to acquire the data, reconstruction algorithms, there are noise levels, illumination types. If the sample is rotated, maybe there are colors. And so there are a lot of variations that you can play with in order to get this diversity. And also, if you want to, you also have many examples from each category. It doesn't help if you only have one image of breast cancer, one image of lung cancer, one of prostate cancer, and so on. It doesn't help you, because these diseases, they first of all can take different shapes, they can take different contrast, they can take yeah, a lot of variations. So you really need to have variations in the data in order to get a good model. Labels is also something that you really need to have good marked up. So meaningful labels, you get them first of all by defining your task and question of what really you want to see. So you can't have too fuzzy descriptions. It must be really clear. This is, say, a tumor, or this is a fault in a mechanical component. And this should also be unambiguous, meaning if I see something in an image with my experience, maybe one of you doesn't see it, then it's not a good label. So it must be possible for all of us to say that at least in this region, we have something that is of relevance. And it should also be possible to derive this label based on the information you have in the image. So for example, insurance policy is nothing that you can see on an X-ray image. So for that, it doesn't help us very much to say that this patient has not so good insurance policy and the other one does. That is not relevant to the X-rays. So we really have to relate it to the labels to what you really can extract from the data. Of course, it's good also to have it quantitative, that you can quantify this information, saying this area is relevant for us. And also sometimes it's good to have it non-obvious. So for example, or actually mostly, saying this image is bright. That's pretty clear. You can get that information. That information you can get just by computing the average intensity. Okay, it's done. So it doesn't help you to tell that. So it's more about what you can see in the images. Then, depending on what you want to do with the data set, you maybe build your data set differently. So there are different purposes in image processing that we can think of: classification, regression, segmentation, detection, and well, there are also other things you can think of. So the classification task is to take an image and put it into some category. Pre-given, of course. So it can't develop a new category from information it doesn't have. And each image should have only one category. Otherwise, you will have conflict. And the categories should be also non-ordered. So there is no priority in which one is better than the other or more related. So the classic example actually is cats and dogs, because in this Imagenet database, there are many cats and dogs. Then is a question to decide from the picture, is this a dog or a cat? And then you can train your method to detect this. And I was also giving a lecture in a machine learning school, and they did just this example, and people tried training first the model, and afterwards I think one was told the dog was a cat, the other one was told the dog was a bird, and it came some quite fun results out of the training, because they did maybe not use the full data set because of time constraints. So again, it's important to have sufficient data in order to take all the variations. Another classification example that we are going to look at a little bit more throughout this lecture today is classifying which number is shown on the image. Here we have the MNIST data again, and you can see that we have the images and the assigned label to each one of them. And you can also see that as they are handwritten, there are pretty great variations. For example, the ones can be tilting in very many ways. And also this one is written in a completely different way. So the question is, is it a 1 or is it a 7? So there are pretty big variations in this data set, as you can see here. Regression is that you take one image, and from that one, you will get some number. So one classic example that is used in many machine learning classes is to estimate the value of a house just by taking a picture of it. Or maybe by looking at satellite image and tell the risk that there will be a hurricane within some given time. A more practical example that I can show a picture of is determining the age of children based on the X-ray from their hand. So in this case, we have this little hand here. It's told to be 100 months, so it's not so little anyway. This is 186 months, 30 months, and so on. And from these pictures, it should be possible to create an estimate on how old the child is. And that is something that is even implemented as a little Kaggle exercise, if you want to look into that. Another very important task is segmentation. And it's related to the classification, but not anyway. So segmentation is about assigning the pixels in the image into different classes. And every pixel will have a label. And examples are if there is a tumor in this image and where it is. That's also important, that with segmentation, you can tell where something is, not only that it is there. Usually you don't want too many objects to classify because that can be very confusing. But again, we have cats and dogs example. So on this picture, there is a lot of cats and a lot of dogs, and even mixed. So it's not only separated by some line, but then you can see here the pink one are the cats and the green ones are the dogs. And that's also a typical task that you can do or train using these data sets. But you can already see here that it's a difference. If you have a classification task, then you only have a written word or a number which you relate to the image. And here, in this case, you have really to go in and mark up different regions within the image. A segmentation example from real data is, for example, you have this microscope image of the nuclei. And here you can see someone has put labels on all the different nuclei in this image. And then that means the training data or the data you have is actually a combination of the acquisition and of an image with the same size, which contains the labels. This is also something that you can find on Kaggle if you follow this link. And detection is yet another thing. It's more about detecting if something is there. It's not so precise as segmentation, but usually it's sufficient to, in the box, to say, okay, we have a car here, or we have a dog here. But it's not really so important to find exact contours, and it can even be overlapping boxes if there are many. And one example here is that you look at different opaque regions within the lungs on X-rays. And then you can mark up different of these regions, saying that this is a suspicious region. Take a closer look into that one. The advantage of doing this is often that it's less time consuming than doing a full segmentation out of the data. Then there are, of course, a lot of other options for doing this. So please feel free to take a look at these examples on the link by following these links. One is, for example, changing features. This horses to zebras. Example is they have a picture of a horse and say, I want to have it as a zebra. And the algorithm is changing it into a zebra. Or you have a landscape picture and say, okay, this is in summer. I want to see what it looks like in winter. And then it automatically modifies the image into something that looks like a winter picture. Another one is into art, also same concept, that you make a picture and then you say, well, I want to have this picture in the way Monet would paint it. And then you get a Monet painting of your neighborhood, for example. So these are different examples of what you can do with these methods. Now, we finally come to your data. So building your own data sets, first point, it's extremely time consuming doing this. And there are not so many great tools. Some are commercial, some are open source, some are very basic. And also the building of your data set is usually very problem specific. So you have your specific question that you want to solve with your project. And therefore, and you maybe don't find also so much data out there in this question in particular in focus. Similar data, similar questions maybe, but your problem may require some extra additions or extra annotations. One way of doing this is plain and simple code-free. So a basic classification puts all images of one type into different folders. So you have one dog folder, you have one cat folder, you have one boy folder, you have one, and so on. And then you probably need to have some kind of database or list to refer to all these. In the regression, then you can take even an Excel file. In one column, you provide the image name, and the next one, you tell what is the regression value you want to reach. If you work on segmentation, then you can also do very simple painting. I'm going to show that as an example soon, using Fiji or actually any paint application. You have your grayscale image, and then with red, you mark up what is relevant, and maybe blue from something else that is relevant. And then afterwards, you have to save this markup. There are some free tools and also some commercial tools. Depending on what your task is, you actually have to take a look into these tools if they fit your purpose. This list can certainly be extended to a lot more, but at least here are some different examples. And the example I mentioned that I did myself was for the lecture I did some weeks ago. In neutron imaging, we have these outlier spots, and they're really annoying because every one of these spots, they produce a line artifacts when you reconstruct the projection data in tomography. And as you can see, there are pretty many, and this little cutout of 256 by 256 are already pretty many of these spots. Some are very obvious, like this one here, for example. It's very easy to detect. Other ones, they are much less clear. And now if you look at this picture, at this markup, you can even see that I wasn't that precise, which actually is a problem too. So for example, these spots here, I missed. They should have been marked up. But marking up this image 2K by 2K took 8 hours to do. And after 8 hours of spot marking, you're pretty tired actually, and you do mistakes. And that's actually the problem also with producing these data sets, that everything boils down to what the person who marks it up, how good they do it. One way to come around this problem is to do simulations, because with simulations you can do geometric models, you can use template models. So more or less you place different patches of what you want to have, maybe from real data too. You can also use physical models, as really doing Monte Carlo simulations, and use them as base for your work. And that can then produce actually arbitrarily much data for you. Well, of course, sometimes there is an end to how much simulation time you can afford, but that's something else. And one example that is, or actually the advantage of these simulation examples is if you have done, for example, a Monte Carlo simulation of your sample, then it's easy to add more or less noise. I mean, the Monte Carlo you just can send in more particles or less particles. If you want to include also these spots that I was marking up, you can create your spots, and then at the same time you will have your spot map generated without even have to mark it up yourself. One very nice example is this paper here. These people wanted to do a segmentation method for detecting faults in ion cast models. And what they did was actually to do a Monte Carlo simulation of a tomography where they included some faults within the data. And then they really knew from the CAD model from this object where they have the faults. And then it was easy also to train, much easier to train and improve the quality of the segmentation afterward. And then there are a lot of other examples that you can look into yourself. And with that, I would say let's take a short break. So see you again in 10 minutes. And then I stop the recording for now.